Okay, so now we're going to talk about something very, very important in medicine, in astronomy, policemen and women catching speeders, all sorts of things. Weather forecasting. It's called the Doppler effect. Has to do with the relative motion between a source of sound and the observer of sound. Okay, so let's say you're standing on Cam Highway, just minding your own business, standing on Cam Highway, and an ambulance with a siren passes you. Now, what do you notice about the frequency? That's like the pitch. What do you notice about the frequency of the sound? I don't care about the loudness, I just care about the frequency. So basically what happens when it passes you, the frequency goes from a high level to a low level. So like, something like that, all right? So here, so this is what I'm saying. So this is where you are, and here's the ambulance approaching, has this high frequency, right? And then when it passes you, it goes, now I'm exaggerating obviously, but, okay? So, all right, so it's just high and then low. So that's called the Doppler effect, okay? So it doesn't decrease continuously, like I say, it just goes bing, bing, all right? Now, again, this is not loudness, this is just a frequency. Now, this is a property of all waves. Now, you may be thinking, so what? Who cares? Well, just patience. We're gonna see who cares, all right? Actually, a lot of people care. All right, so, oops, okay. Oh my gosh, there are all these formulas. So I certainly would not expect you to memorize these, but I will certainly have them on the, the equation sheets for the exam, but you need to know how to use them. So these formulas just tell you how the frequency, either decreases or increases depending on what the ambulance is doing or what the source of sound is doing. So these are the Doppler effect formulas. Okay, so here, let's say that the source, like an ambulance, source of sound, these are just for sound waves. The source of sound is approaching a stationary observer. Well, what's going to happen is that the frequency is going to go up. All right, so we have F positive, which is supposed to signify the frequency increases. Okay, now, you got to know what these things are. So F0 is the frequency of the source at rest. So if I had an ambulance at rest with a siren on, F0 would be the frequency of that siren. Now here, careful, Vs is the speed of the source. V0, or VO I guess, is the speed of the observer. So it kind of stinks, because you think Vs, the speed of sound. No! Right? V is the speed of sound. And typically it's like 343 meters per second. So again, Vs, speed of the source, all right, relative to the observer. V0, speed of the observer, whatever, relative to the source. Okay, so here, so F plus, we know that the frequency is going to increase. So it's F0 divided by 1 minus this. So in other words, the denominator is getting smaller, so the fraction has to get larger. Okay, if the source is moving away from the observer, that was my initial example, the frequency decreases because now the denominator gets bigger, right? So this thing gets smaller. And then you also have this, right? All right, so this is the ambulance approaching a stationary person, ambulance moving away from a stationary person. Okay, there's also this, observer approaching a stationary source. So a person walking towards a stationary ambulance. The frequency increases, that's why there's a plus. Or observer, a person walking away from a stationary ambulance. The frequency decreases. All right. Yeah. So, let's see. Okay, so we're going to do an example. Oh, this is a great example. All right. So it's kind of too bad this is online, because if we were face-to-face, I'd have half the class do that and half the class do that, and we'd learn a whole lot. But since we don't do that, we just do it. Just do it. Okay, let's read. Okay, an ambulance emitting sound at 300 hertz, the frequency, right, moves away from a stationary observer at 30 meters per second. What is the frequency of sound heard by the stationary observer? Okay, so you got it? So stationary person, ambulance is moving away, right? So the frequency decreases. Now this one, an observer moves away at 30 meters per second from a stationary ambulance emitting sound at 300 hertz. All right, so think about it. So look at A is you have a stationary person, right? And the ambulance, sorry guys, the ambulance is moving away at 30 meters per second, right? That's one. Number two, you have, let's see, yeah. So here's the ambulance, let's say, and make it the other way around, who cares, right? So stationary, right? Stationary, and now you have the observer moving away at 30 meters per second. Now, come on! Isn't this equivalent? I mean, what's the difference? Here, the guy is stationary, ambulance is moving away. Here, the guy is moving away, ambulance is stationary. Isn't that the same thing? So you'd think it would be the same answers, right? Let's see. Okay, let's see. All right, so for this one, the ambulance moves away from a stationary observer. So we have a source receding from a stationary observer. So we have this formula. So we have F minus equals F0, 1 plus V source over V. Okay. And that is equal to F0 is 300 hertz. 1 plus, okay, Vs is 30 meters per second, right? The velocity of the source, 30 meters per second. And V is the speed of sound, 343 meters per second. All right, and I promise you when you do that, you get 275.9 hertz, okay? So just like we expected, right? You know, the ambulance is moving away from the person, and so we expect the frequency to decrease. It did, right? It went from 300 to 276. Okay, now that's number one. Let's do number two. Okay, number two. An observer moves away from a stationary source. So observer receding from a stationary source. So we want this one. So again, F minus, no kidding, F minus 1 minus V O, or who cares, over F0. All right? Okay, so 1 minus, now, what's the speed of the observer? 30 meters per second. 30 meters per second. What's V? Speed of light, speed of sound. What's F0? 300 hertz. Right? No, wait a minute, that's wrong. Times. Oh, yeah, I knew that was wrong. Times F0. So 1 minus 30 meters per second over 343 meters per second times 300 hertz. And that comes out to be 273.8 hertz. Now, you should look at those numbers and you say, wait a minute, that's totally insane. Because this is exactly the same as this, right? This one, I mean, who cares? This one, the observer, like I said before, is stationary, the ambulance moves away. Well, I'll just look at it from the other viewpoint. This one, the ambulance is stationary and the guy moves away. It's the same thing, right? Well, you got to be careful. Okay, the relative velocity between the person and the ambulance is the same. Granted, 30 meters per second. But the thing is important is that the Doppler shifts are different. The Doppler shifts are different. And because the velocities, the important velocities, are the velocities relative to air. Okay, that's what's important. What's important is what is the velocity relative to air. Okay, so like here, for number 1, the ambulance, which is the source of sound, is moving relative to the air, right? But for this one, the ambulance, the source of sound, is stationary with respect to the air, okay? So that's what's important. What's important is not the relative velocity between the source and the observer. That's not the important thing. The important thing is the velocity of the sound relative to air. And that's different for this one and this one, okay? So basically, I guess the bottom line is when you have questions like this, don't philosophize. Just use the equations, and then you get them right. All right. Now, I told you that, or I said that this Doppler effect is true for any kind of wave. Well, light acts like a wave. So, you know, these equations were for sound. We have different equations for light. Oh, sorry. I gotta read that. Sorry. So this has to do with this problem we just did. Mechanical waves, like sound, move through a medium, and the Doppler effect depends not just on how the source and the observer move with respect to each other, but also on how they move with respect to the medium, air, for sound. Okay? All right, whatever. All right, so these are the Doppler equations for light. Notice there's only 2, right? All right, so this is for approaching light. This is for receding light. Okay, and if light is approaching, the wavelength gets smaller, and that's called a blue shift. I'll show you why in a minute. If the object of the light is receding, the wavelength gets larger. That's called a red shift. Okay, Vs is the speed of the source, and c is the speed of light. So what's this blue shift, red shift thing? So this is from that electromagnetic spectrum slide, but I'm only showing, I'm kind of blowing this up, the visible. So you can see for long wavelengths, it's red, and for short wavelengths, it's blue, or ultraviolet, purple, call it blue, all right? Okay? So that's what this is all about. Okay? If the wavelength gets shorter, they call it a blue shift. If the wavelength gets longer, it's a red shift. All right, so this is used in astronomy to measure the speed of objects and the direction of objects. So here, this is how it works. So on Earth, people, they look at different elements, barium, calcium, hydrogen. They actually look at tons of different elements. And they heat them up or they do something to them so they emit light. And what we know is that every element has a unique spectrum. What are you talking about? So this is barium. So you heat up some barium until it starts glowing, starts emitting light, and it only emits light at specific wavelengths. It's kind of like a fingerprint, right? And we'll talk about this when we do later on. We'll give you the reasons for this. So all barium, every single barium element in the world, or atom, if you heat it up, it emits light at these specific wavelengths. So this is like the fingerprint for barium. Calcium looks like this, hydrogen like that, and sodium like that. Okay? So you can always identify the elements just by looking at their spectrum. Okay, now this they do in the lab, so the elements are at rest. So then what they do, then they take their telescopes and they look to like a star. Let's say the star is moving away or toward or who knows what. And they look and they see the spectrum, right? So this is what they would see on Earth, at rest in the lab. And then they see the spectra from something moving. And they can measure the wavelength here. They can measure the wavelengths here with a spectrometer. And so they notice that the wavelength here has been shifted. It's been Doppler shifted. So what they do then is they use the Doppler formulas to figure out the speed of the source. So you can actually figure out how fast galaxies are moving, stars, all sorts of cool things. So it's kind of neat. And I'm not going to go into it, but they've used this Doppler technique to measure the speed of galaxies that are far away. And astronomers have learned that when you look far enough, that all of the galaxies, no matter where you look, are moving away. And so I'm not going to explain it all, but basically that indicates that the universe is expanding. So the Doppler shift was used to show or to prove that the universe is expanding. So do you think the Doppler shift is important in astronomy? Well, yeah! Super, right? Super important. Okay, in a hospital, the Doppler effect is used to measure the blood flow, right? The blood flow, how fast the blood is going in people. You may have gotten a speeding ticket once in your life. Most likely, the police, maybe they use a radar gun or something that uses the Doppler effect. Pretty cool. All right, now we're going to see another short video.